Every time your phone routes a trip on Google Maps, populates a social media feed, or requests a website halfway across the globe, it is navigating a vast web of data points. To process that information instantly, a computer cannot treat each network as a unique puzzle. It treats them all as identical mathematical structures. This equation represents a graph. It is the formal mathematical definition of a network, stating that any graph, G, is entirely defined by just two sets, a set of vertices, V, and a set of edges, E. Before you can write code to search an AI decision tree or route packets through a system, you must understand this mathematical grammar. A CPU does not understand the concept of cities on a map or friends on a timeline. Stripping away the real-world context and reducing those relationships into formal sets of vertices and edges allows a machine to solve these problems mathematically. Look at this single point on the grid. This is a vertex, sometimes called a node. It represents a singular entity, a specific person, a router, or a city. To map a relationship between any two distinct vertices, we establish an edge. By plotting these cyan lines, we explicitly define our mathematical sets, 4 vertices in set V and 4 exact connection pairings in set E. Counting the total number of vertices gives us the order of the graph. Here, the order is 4. Tallying the total number of edges gives us the size. In this structure, the size is also exactly 4. Order and size provide the specific variables a software engineer uses to calculate the memory limits and computational complexity of any algorithm applied to the network. The structural and mathematical rules of a graph change based on the directionality of its edges. On the left is an undirected graph. The relationships here are symmetric. If node A connects to node B, B is inherently connected back to A. This is how a Facebook friendship operates. The connection requires mutual agreement and flows both ways. On the right is a directed graph, or digraph. These connections are asymmetric. Node A pointing to B carries no guarantee that B points to A. An Instagram follow works this way. The relationship is strictly one way, dictated by the arrow. Because of this asymmetry, a search algorithm traversing a directed graph will hit dead ends and forced one-way routes not found in undirected graphs. Identifying whether a problem requires a directed or undirected graph is a prerequisite for building the search or routing logic in code. To measure local connectivity within an undirected network, we use a metric called degree. This is simply the total number of edges connected directly to a specific vertex. Because 3 lines touch node C, its degree is 3. In a directed graph, this metric splits to account for flow. We tally the incoming arrows to find the in degree, and the outgoing arrows to determine the out degree. For any undirected graph, the sum of the degrees of all vertices will always equal exactly twice the total number of edges. This is known as the handshaking theorem. We can check this by looking at our current structure. Node A has a degree of 2. B and C each have a degree of 1. Their sum is 4. We have a total of 2 edges. 2 times 2 is 4. The equation balances. This occurs because every edge serves as a bridge between 2 distinct vertices. Every edge added to the graph contributes exactly twice to the total sum of degrees. Because the sum of degrees is exactly double the edge count, it provides a mathematical constant used to validate a network's data structure. Tracing a valid sequence of connected vertices from a starting point to a destination yields a path. The length of that path is measured by the exact number of edges traversed. If that path loops back so that the starting vertex and the ending vertex are the same point, it forms a cycle. When every vertex is reachable from every other vertex, the graph is connected. If the structure fractures into isolated pieces with no bridging edges, it is a disconnected graph. Algorithms that can detect hidden cycles or map disconnected fragments allow engineers to prevent infinite loops in code and identify deadlocks in physical networks. This logical framework defines how graphs function. The vertices and edges establish the physical structure, while directionality, degree metrics, and cycles dictate the rules of navigation. However, this geometric model is built for human reasoning. A computer processor has no native mechanism for storing circles and connecting lines in its memory registers. To apply this theory, the structure must be mapped directly onto physical computing hardware. Visual properties must be translated into organized data structures that the operating system can allocate memory for and manipulate. Mastering these representations, adjacency matrices and adjacency lists, converts theoretical mathematics into the physical memory layouts used in modern software engineering.